So far, what we've spent a lot of time doing is finding ways, once we've modelled the system, finding ways to say, well, if I apply an input of some type, like a step or a ramp or whatever it is, to that system, what's it going to do? And last week we looked at typical responses for first and second order systems to our standardised inputs, particularly the step, because that's the one that's easiest to draw pretty much. If you think about what we were looking at there are transients. Yeah. The step input by its nature produces a transient response that then settles down to some value, and in the case of a stable system is some kind of finite number. Yeah, we drew the graph and the response just kind of wobbled into a steady state, into the final value. So sometimes you'll be in a position where you've got a model of a system as a transfer function and you want to apply some kind of input to it, but perhaps you actually don't care what the transient behavior is. All you want to do is to figure out where does it get to eventually. Okay. So it seems a little bit over the top, working out the full solution for that response, telling you all about the transients and the overshoots and the oscillation and all the rest of it, when all you actually want to know about is what's the final value. Okay, where does this thing end up? Thankfully, we can do that by using a little bit of a shortcut process. And that shortcut process is based around what we call the final value theorem. Okay. So you've got a model of a system as a transfer function, you've got the input you're applying, maybe a step or a ramp, so you can do the same thing, output equals input times transfer function, but instead of completely calculating it, let's shortcut the process to find the steady state value. Okay, and here it is. Okay. The limit of any function in time as the time approaches infinity, in other words the final value, is the limit of big F is any function in the Laplace domain times the Laplace operator as we make the S terms tend to 0. Okay, so I've got my transfer function multiplied by my input quantity, so I've got my f of s, that's my s function that's describing the output. If I want to find out the final value, all I need to do is to multiply it by s and then make all the s terms equal to 0. And what I'll get out of that is the final value. Here's an example, okay, so if I've got a transfer function 5 upon s plus 3, so it's a first order system, and the input I'm interested in is a step input of amplitude 3. So the output quantity, same as we've done before, is the input times the transfer function. All I'm suggesting to you is using the final value theorem. If all I'm interested in is where does it finally end up, I need to take my Laplace function, multiply by s, and make all the s terms tend to 0. So this would become 15s over s squared plus 3s. Okay. Bit of cancellation to tidy it up, and what I end up with is 15 upon 3, which is 5. Okay. I get no information at all about the dynamic or the transient response of this system, but I do know where it ends up. Okay, and sometimes that's what I want to find out in a hurry. One way to imagine what's going on here, why do we set the s term to 0? What does the s term represent? When you're taking your first steps between a time function and a Laplace function, where does the s come from? When we first started off with the differential equation and we transferred it to the Laplace domain, what is it that we replace with s? differentiation with respect to time, d by dt. Yeah? If you think about these problems, if you make the d by dt term tend to 0, what you're saying is things have stopped changing. Because the d by dt, the rate of change has become nothing. In other words, it's come to a steady condition. So in a sense, that's what's going on here. We're looking at the condition when all the changes have stopped.